The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Okay, I'm going to continue our blitz through a review of thermodynamics, and we're going to start right now talking about spontaneous change. And you all know what spontaneous change means. It means some change that occurs without intervention. Spontaneous change has a directionality to it. So, for example, if you put a rock near the top of the hill and you let go, it rolls down, it doesn't roll up. If you put a warm body next to a hot body, the heat flows from the hot body to the cold body and not the other way. If you, for example, have a bulb of gas here and a stopcock and an empty bulb, you open the stopcock, that gas flows from the high pressure region to the low pressure region, and it doesn't go the other way. However, spontaneous change doesn't have to be fast. You know that if you take a bottle of ketchup, when it used to be a glass bottle, which you couldn't squeeze, and you turn it over, well, that ketchup has a spontaneous tendency to flow out, but it doesn't have to be fast. Okay. So what is in chemical reactions the key to spontaneity? Is it the exothermicity? Well, certainly iron rusts, right? You don't have to do anything to make it rust. Very exothermic reaction. Delta H about 824 kilojoules per mole. If you have an acidic stomach and you then ingest something that's a little bit more basic, well, this reaction goes, it neutralizes that acid. Also an exothermic reaction. You didn't have to do anything other than drink the more basic solution. This reaction here, this hydrolysis of ATP to ADP, adenosine diphosphate, proceeds in every cell of your body. And you don't have to do anything to make that go. Hey, that's an exothermic reaction. But what about an endothermic reaction? How about this reaction? This is ammonium nitrate dissolving in water to make ammonium ions and nitrate ions. The delta H for this reaction is positive, plus 25.7 kilojoules per mole. It's an endothermic reaction. Is this reaction spontaneous? Well, yes. We're going to do an experiment anyway, all right? And the experiment we're going to do is you're going to be given one of these cold packs, and the TAs can start distributing them. And what you've got to do is you've got to find the little pouch inside the cold pack that contains the water. You got to press on that, allowing the water to disperse in the material. And you'll see if the reaction goes. If it goes, that cold pack better get cold, because this is an endothermic reaction. It's going to remove some heat from the environment. Some of you will get hot packs, and we'll see if that's spontaneous. Okay. Is an endothermic reaction spontaneous? Yes. Is an exothermic reaction spontaneous? All right. Is delta H the key to spontaneity? No. What is? Delta G. Right. Okay. So delta G is the key to spontaneity. You already know that when delta G is negative, you have a spontaneous reaction. When delta G is positive, you have a non-spontaneous reaction. And very importantly, when delta G is 0, that's when you're at equilibrium. That's what we're going to be talking about in just a few minutes, when delta G is equal to 0. These are the conditions, of course, for constant temperature and pressure. All right, so delta S here in this expression for delta G. delta S is the change in the entropy. It's a measure of disorder. When delta S is positive, we have an increase in the disorder. When delta S is negative, we have a decrease in the disorder. Now, where do these conditions come from? Well, you're going to talk about that in exquisite detail in 560. All right? But I want to give you a physical understanding for what delta G is. And that's this. Suppose you have an exothermic reaction. It turns out that not all of that exothermicity, not all of that enthalpy can be released to the outside world to do useful work. Some of that enthalpy is actually caught up in the product molecules, or can be caught up in the product molecules. Some of that enthalpy gets stuck in the product molecules. It gets stuck in the vibrations and rotations of the product molecules, in the internal degrees of freedom. And it is that energy that is not available to do useful work. So for some exothermic reactions here, the amount of energy that is available to do useful work is something smaller than delta H. It's delta H minus T delta S, where T delta S then is a measure of how much of that enthalpy is stuck in the internal degrees of freedom of the molecule. And so this delta G is called the free energy, because this is the amount of energy that's free to do useful work. Okay? That's what delta G is. So for example, if you go home and you turn on your gas stove, oxidize some methane, burn some natural gas to heat up the water in your pasta for your pasta, that delta H here, very negative. But let's now calculate delta G. Well, to do that, we need to know what delta S is. Delta S, I'll show you in just a moment here. It's the change in the entropy. We can calculate that. But knowing delta S then, we can plug in the delta H and the temperature. And what we find is that delta G here is less negative than delta H. So not all of this enthalpy, not all of that energy is available to the outside world to do useful work. Some of it in this reaction gets trapped or caught in the internal degrees of freedom of the molecule, and it's not available to do that useful work. Delta G in this case is less negative than delta H. All right, but let's take the eat, breathe, exhale, P reaction, the oxidation of glucose going on in every cell of your body. Well, this reaction, also very exothermic. But let's calculate delta G for this reaction. Well, first of all, we need delta S. From that, we can calculate delta G. And in this case, what do you see? Well, in this case, you see that delta G is more negative than delta H. Hey, in this exothermic reaction, we're getting back all of the enthalpy and then some. We're getting back even more. And that extra energy is coming from the energy that is tied up in the internal degrees of freedom of the reactants. In this reaction here, delta S is positive. We're increasing the disorder. If we increase the disorder, there's less ways, there are fewer ways to tie up energy in the internal degrees of freedom of the molecule. When we increase the disorder, that's what happens. And so we're getting, your body's figured out how to get back all of that delta H and then some, right? We're getting that energy out that is locked up in the reactants, in the internal degrees of freedom of the reactants. Okay. So that's a physical feeling there for what delta G is. All right, entropy for a reaction. The entropy is calculated from the absolute entropies of the products and the reactants. And so what you need are the absolute entropies for each one of the products multiplied by the appropriate stoichiometric number. You sum them all up. And you do the same then for the reactants. The absolute entropy of each one of the reactants multiplied by that stoichiometric number, sum them up, subtract it to, that's the entropy change for the reaction. Now, one thing I do want to point out is that in the case of entropies here, these are absolute entropies. That's rather unusual in thermodynamics. In thermodynamics, usually we look at changes in energies. But here we're talking about absolute entropies. That is a consequence of the third law of thermodynamics. You'll see how that arises again in 560. All right, but right now we're going to use it to calculate the entropy for a reaction. All right, and some reactions here are completely entropy driven. For example, if you melt ice, hey, this is an endothermic reaction, 6.95 kilojoules per mole in going from solid water to liquid water. You have to put in energy into the system to do that. But you know that this reaction occurs spontaneously. If I had a cube of ice here, hey, it would melt. This reaction is entropy driven. Why? Well, let's look at it. Let's calculate delta S for that reaction. You need the absolute entropy for water in the liquid phase. That's the product. Minus then the absolute entropy for water in the solid phase. The difference between the two is positive. We increased the disorder. There are less ways to tie up energy in liquid water than there are in a solid water, in ice. Right? And that fact is going to make this reaction then spontaneous. Right? 6.95 positive for delta H minus T delta S. This term here, T delta S, now is larger in absolute magnitude. Therefore, delta G is negative. This reaction is spontaneous. It is certainly here entropy driven. Okay? Okay. Now, the other concept that I want to talk about is the free energy of formation. The free energy of formation is analogous to what we talked about last time, the enthalpy of formation. The free energy of formation is the free energy for a reaction that forms 1 mole of a compound from the elements in its standard, in their most stable form in the standard state. And our standard state is 1 bar. Okay. The free energy of formation here is tabulated like the heats of formation. So you can find tables of free energy and enthalpy of formation for all molecules. However, unlike the enthalpy of formation, the free energy of formation can also be calculated easily by you, and that is the following. If you know the free energy of the enthalpy of formation for some reaction, or for the reaction that defines the enthalpy of formation, and you know what the entropy change is for that reaction that defines the enthalpy of formation, well, then you can calculate the free energy here of formation. Okay? So you got 2 choices in the case of the free energy of formation. You can look it up, or if you know what delta H sub F is and delta S are for the reaction that defines the free energy of formation or the enthalpy of formation, you can calculate the free energy of formation here. Okay? Okay. Now, here is a reaction that forms 1 mole of CO2. And the delta G for this reaction is minus 394 kilojoules per mole. the delta G for this reaction is defined as the free energy of formation for CO2. It is so because we're forming 1 mole of this molecule from the elements in their most stable form in the standard state. The most stable form of the element carbon is graphite. The most stable form of the element oxygen is molecular oxygen. Okay? But what's important about the free energy of formation here is that it's a measure of a compound's stability relative to decomposition to its elements. So for example, right here, the free energy of formation of carbon dioxide, that's negative. What that means is that CO2 is thermodynamically stable relative to decomposition into its elements, right? Because delta G for this reaction is written is negative. The reaction is spontaneous in this direction. It is not spontaneous in the reverse direction. That is, the decomposition of CO2 to its elements is not a spontaneous process, and therefore we say that CO2 is thermodynamically stable relative to decomposition into its elements. Okay? All right, so if you have a free energy of formation for a molecule that's negative, it's thermodynamically stable. But if you have a free energy of formation that's positive, well then that compound is not thermodynamically stable relative to decomposition to its elements. For example, let's look at benzene here. Right? Here's a reaction that forms 1 mole of liquid benzene from the elements in their most stable form in the standard state, graphite and molecular hydrogen. The free energy of formation for this benzene is positive 124 kilojoules per mole. That means that this forward reaction as written is not spontaneous. However, the reverse reaction is spontaneous because delta G is minus 124 kilojoules per mole. And so we say benzene here is thermodynamically unstable relative to its elements. All right? Okay, but even though you might have a reaction here that is spontaneous, that is the reverse reaction. You have a delta G of formation that's positive, meaning the reverse reaction is spontaneous. Even though that reverse reaction may be spontaneous, it also could be very, very slow, right? When was the last time you saw a pint of benzene decompose into graphite and hydrogen? You haven't seen that. I haven't seen that, and I am a lot older. Okay, so what this means is that even though you might have a thermodynamic tendency to decompose, it doesn't mean that it's going to happen because there's a question of the rate of the chemical reaction. So we have 2 different terms to describe the thermodynamic tendency and then the kinetic tendency. And these terms are the following. We call a molecule stable or unstable when we're referring to the thermodynamic tendency. That is, when we are referring to delta G, or the free energy of formation. If it's negative, the molecule is stable. If it's positive, the molecule is unstable relative to decomposition. However, we also have to consider the rates. And we've got another term to describe the rates, and that is labile and non-labile. If a molecule is non-labile, what that means is that the rate at which the thermodynamic tendency is realized that rate is very, very slow. So benzene, for example, it's thermodynamically unstable relative to decomposition into its elements, carbon and hydrogen, but it's non-labile. The rate at which that reaction happens is just too slow to be of any practical interest to you. However, if this decomposition reaction occurred very readily, then we would call that molecule labile, all right? That is, the rate of the decomposition is something that is going to affect your ability to handle that particular compound or that molecule. Okay? Okay. Now, like the free energy of formation, or like the enthalpy of formation, sorry, the free energy of formation can also be zero. So last time we talked about how the enthalpy of formation for hydrogen, oxygen, chlorine, xenon, hey, all of that had zero enthalpy of formation. Well, all of these molecules have zero free energy of formation, right? Because they are all in the most stable form already in the standard state. The free energy of formation of bromine liquid and mercury liquid, hey, that free energy of formation is zero because they are in the most stable form at the standard state. The free energy of formation of carbon in the form of graphite, sodium solid, iron solid, iodine solid, hey, those free energies of formation are all equal to zero. But the free energy of formation here of bromine in the gas phase, that free energy of formation is not equal to zero because bromine gas is not the most stable form in our standard state. Liquid bromine is. So it's going to take energy to produce bromine gas. So delta G of formation is not going to be zero. Likewise, the free energy of formation of diamond here, hey, that's not equal to zero because carbon in the form of diamond is not the most stable form of carbon. Graphite is. So this is going to take energy to form that configuration of carbon. Okay? So free energies of formation, very important in terms of understanding the thermodynamic stability of molecules. All right, just a review here. If you want to calculate delta G for a reaction, what can you do? Well, you can take the free energy of formation for each one of the products, multiply it by the appropriate stoichiometric number, since those free energies of formation are given per mole, add them all up, and then do the same thing for the reactants. Free energies of formation for each of the reactant, stoichiometric number, add them all up, subtract the two. That's the delta G for your chemical reaction. Notice, like delta H for the chemical reaction, which you calculated from the differences in the heats of formation of the products and reactants, note this is products minus reactants. This is different from when you calculate delta H, for example, from bond enthalpies. That was reactants minus products. All right, something to remember. Okay, but again, in the case of delta G, we can calculate it from knowing the free energies of formation of the reactants and the products, but we can also calculate it from this expression, right? If, for example, you know the enthalpy change for a reaction, and you know the entropy change for a reaction, you can calculate the free energy change from these two quantities. All right, so you got two choices to calculate the free energy change of some chemical reaction, depending on what information you know or is given to you. All right? Okay. Well, now I want to talk kind of briefly about controlling the spontaneity of a chemical reaction. And to do so, I'm going to talk about this molecule, which is sodium bicarbonate. Sodium bicarbonate is better known as baking soda. It is what you put into some batter of some soft baked goods that you want to make. And what happens is that the sodium bicarbonate decomposes. And two of the products are gases, CO2 and water. And so in your batter, what you get are these bubbles of CO2 and water. And what happens is that the dough starts to harden around these bubbles. And then, of course, eventually the CO2 and the water are completely driven off. But what that leaves behind in the batter is a very porous structure. So porous that after you remove it from the oven, you can actually put your teeth into it. Have you ever left out the baking soda in some soft baked goods? You can't get your teeth into it, right? So this is an important reaction. Okay, but this is a reaction here that's very endothermic. It does increase in the entropy, but at room temperature, this reaction has a positive delta G. This reaction does not proceed. It is non-spontaneous in the forward direction as written. And you know what? That's good, because you don't want this reaction to start when your batter is still on your kitchen counter. You want it to start when it's in the oven. So what happens as we raise the temperature here? Well, we have the same, for the purposes of what we're going to do, we have the same delta H and delta S. But now when we calculate delta G, the temperature here is going to be our baking temperature of 350 degrees Fahrenheit. And now what you see is that delta G is negative, minus 14 kilojoules per mole. Hey, all of a sudden this reaction became spontaneous, and we made it spontaneous simply by increasing the absolute magnitude here of T delta S, right? We increased it by increasing the temperature in this case. We made it spontaneous by raising the temperature. All right, so for some reactions we can do that. We can find a temperature at which the reaction will be spontaneous. Let's look at the particular conditions. All right, so delta G here is a linear function of the temperature. So let me draw that for this particular case, for the sodium bicarbonate decomposition. The slope of this line for this reaction here is, of course, minus delta S. The intercept is delta H. And now let me just draw a 0 here. What I want you to notice is that there is some temperature right here. Right? There is some temperature which I'm going to call T star. There is some temperature at which the sign of delta G changes. You see that below T star, delta G is positive. Below those temperatures, such as room temperature, for the sodium bicarbonate decomposition, delta G is positive. We have a non-spontaneous reaction. Above some temperature, delta G has become negative. We have a spontaneous reaction. We can calculate the value of this T star, where the spontaneity switches, by setting delta G naught equal to 0 and then solving for T star. So let's do that. I rearrange this to give me T star is equal to delta H over delta S. For this reaction, I know the values of delta H and delta S. And for this reaction, that value of T star is 406 Kelvin. So your oven has to be higher in temperature than 406 Kelvin if you want to make some baked goods that you can put your teeth into. Okay, so for some reactions, and in this particular case here, for a reaction that is endothermic, delta H greater than 0, and for a reaction in which we have an increase in entropy, well, that reaction is spontaneous whenever the temperature is above some temperature T star. Okay, but we also have reactions which are exothermic, delta H less than 0, and reactions in which the entropy decreases. Delta S is 0. Delta S is less than 0. And I've plotted that line here, delta G versus T. Now, for the opposite condition, we have the opposite slope because delta S has changed sign. In this case, the reaction will be spontaneous whenever the temperature is below some temperature T star, right? And you can see that by looking at the relative signs in this expression. If delta H is less than 0 up here, then we have a negative quantity right here. And since delta S is less than 0, we have minus times a minus, that's a plus. And so this term here is positive, this term is negative. And so this positive term better not be in absolute value very much larger than delta H here, right? If it is, then we're going to have a positive delta G, but if this term is small compared to the absolute value of delta H, well, then we will have a spontaneous reaction at low temperature. So you want to keep this term small. So that's why it's spontaneous when T is less than T star. Okay. But we can also have reactions that are exothermic and reactions in which the entropy increases. Well, in this case, you got the best of all worlds, right? In this case, this reaction is spontaneous at all temperatures. You can't adjust the spontaneity of this reaction by temperature, all right? This is always going to be negative. Delta H is negative here, minus T delta S. This is going to be a minus a positive number. A negative minus a positive number is always a negative number, always spontaneous. And then finally, we can have a condition where we have an endothermic reaction, delta H is greater than 0, and where the entropy decreases, delta S is less than 0. In this case, the reaction is never spontaneous, no matter what temperature you do. You can't adjust that non-spontaneity with temperature. Delta H here, you can see that, it's going to be positive. And then since delta S is negative, we have a minus times a minus, that's positive. Delta G is positive at all temperatures. Okay, so we have failed to adjust the spontaneity with temperature for some reactions that are endothermic and in which the entropy decreases. Okay. Now, what we've been talking about are values of delta G that are our standard state. We've been talking about delta G here, delta G naught, 1 bar pressure. That's what we've been talking about. What that means is that the delta G for any reaction, the delta G naught for any reaction, means that we've got 1 atmosphere each of the products and the reactants. That's what delta G naught means. All right? So take our famous reaction here, argon-boron, argon plus boron going to carbon plus deuterium. All right? Let's take this reaction. When I give you a delta G naught for this famous reaction, what that means is that that's the delta G naught when the partial pressure of the reactant A is 1 bar, and the partial pressure of reactant B is 1 bar, and the partial pressure of reactant C is 1 bar, of product C is 1 bar, and the partial pressure of product D is 1 bar. Hey, that doesn't seem real useful, right? Because certainly, say you were going to start a reaction, and you just start it even with 1 bar of A and 1 bar of B. Well, this is not the delta G under those particular conditions, right? So we have to be able to calculate delta G under any conditions, not just our standard state conditions. And that's what we're going to do with this expression here. We're going to be able to calculate a delta G at any time during a reaction. We can stop a reaction, and we can measure the partial pressures of the reactants and the products present. And we can get from that then a delta G for the reaction at that particular point. All right? That's what we're going to do here. All right. So what have I got written here? Well, I got delta G is equal to this delta G naught, the standard state delta G, plus RT ln of the partial pressure of product C over some reference pressure raised to the appropriate stoichiometric number, times the partial pressure of the other reactant divided by some reference pressure raised to the appropriate stoichiometric number. And that's all over the product of the partial pressure of A over that reference pressure raised to the appropriate stoichiometric number times the same for reactant B. Okay? What this ratio here of partial pressures is, or what it's called, is the reaction quotient Q. It is the ratio of the partial pressures present at any time during the reaction. Not necessarily at equilibrium, at any time during the reaction. Okay? That's what our Q is here. And so in this way, with this expression, we're going to be able to calculate what delta G is for the reaction at any time outside of this special standard state of 1 bar pressure for each one of the reactants, 1 bar partial pressure for each one of the products. Where this expression comes from is again discussed in exquisite detail in 560. Okay? You'll see where it comes from later. But right now we're going to use it to calculate delta G at any time during the reaction. Okay. But now let me point out that our reference pressure right here is 1 bar. So what I'm going to do is I'm going to substitute a 1 in here for each one of the reference pressures so that my reaction quotient's going to look like this. And I didn't put in the bars because what you're going to do is you're going to put in the pressures in bars, and then the reaction quotient will be just fine. All right? So you've got to use bar pressure here since that's our standard state. That's our reference pressure. Okay. So now, keep this in mind. This is important. We're going to use this again in just a moment. Let's start talking about the equilibrium constant. Here is our famous A plus B going to C plus D reaction. We already said if delta G for this reaction is written is negative, hey, then that forward reaction is spontaneous. If delta G for that reaction is positive, for the reaction is written, what that means is then the reverse reaction is spontaneous. And now, very importantly, if delta G is 0, then we're at chemical equilibrium. Hey, notice this is delta G equal to 0. This is not delta G naught equal to 0. Big difference here. Okay, this is delta G equal to 0. Then we're at equilibrium. So what I'm going to do is I'm going to bring back my expression that allowed me to calculate delta G at any arbitrary pressures of the reactants and the products. And I just said that equilibrium here is defined by delta G being equal to 0. So I'm going to plug in a 0 right in there. Okay? If that's the case, then I'm going to rearrange this equation. I'm going to bring delta G over to the other side. And that's what I do here on the next slide. And I have delta G naught is equal to minus RT ln of this reaction quotient. Okay, now we have a special condition here. And that is when delta G is equal to 0, when we are at thermodynamic equilibrium, this reaction quotient has a special name. And that special name is the equilibrium constant, K. Right? This reaction quotient is equal to the thermodynamic equilibrium constant, and it is so only when delta G is equal to 0, not delta G not equal to 0. Okay? Okay. So we get the equation delta G naught is equal to minus RT ln of K. That's where this particular expression comes from. So the reaction quotient is equal to K when we are at thermodynamic equilibrium. All right, so now what we're going to do is we're going to set up some equations here that are going to allow us to quickly tell when our reaction is at equilibrium. We're going to compare Q to K. Let's do that. So here's that general expression I had that allowed me to calculate delta G at any arbitrary pressures of the reactants and the products. Here's the expression, delta G naught, at equilibrium. Delta G naught equal minus RT ln of K. What I'm going to do is I'm going to substitute this delta G naught into here, right in there. All right? Let me do that. I'm just going to plug it right in. So I have minus RT ln of K plus RT ln of Q. So now I've got the difference between two logs. The difference between two logs is the log of the quotient of those arguments of the logs. All right, so delta G then is RT times ln of Q over K. All right. Now, remember what Q is. It's this ratio of instantaneous partial pressures. So, if we got a reaction running and we somehow measure the partial pressures at some time, and we find that Q, we calculate the reaction quotient from that, and then we find that Q is less than K, the equilibrium constant. What that means is that we have fewer products present than equilibrium says we should have, because Q is less than K. If that's the case, then what's going to happen is that the reaction is going to proceed in the forward direction in order to make more products so that Q can get to the point of being equal to K. You can also see that up here. When Q is less than K, we have the log of a number that's going to be less than 1. The log of a number less than 1 is a negative number. So when Q is equal to K, delta G is going to be negative, meaning the reaction as written is spontaneous in the forward direction. All right? That's what our equilibrium says, wants to do, wants to make more products. On the other hand, if we have Q greater than K, well then that says that we've got too many products compared to what equilibrium says we should have. And of course then, the reaction is going to run in the reverse direction. It's going to try to use up those products and make more reactant. You can also see that by this expression. When Q is greater than K, we're going to have the log of a number that's greater than 1. That's going to be positive. Well then, if delta G is positive in the forward direction for the reaction is written, well then it's the reverse reaction that's going to be spontaneous. Okay? Another way to look at it is shown here. Suppose we are in a situation where Q is less than K. All right, so I'm plotting here Q as a function of the time in the reaction, and I'm starting out here at t equals 0, and Q is less than K. If Q is less than K, it means that we have fewer products than what equilibrium tells us we should have. The reaction is going to proceed in the forward direction. It's going to proceed in the forward direction so that Q increases, so that Q will increase to the value of K, so that we can attain equilibrium. On the other hand, if we've got a situation where we start a reaction, but Q is greater than K, in that case, we started the reaction by putting all the products in instead of the reactants. All right? When Q is greater than K, it says we've got more products than equilibrium says we should have. What's going to happen is that the reverse reaction is going to proceed. It's going to try to use up those products, right? So that we attain this ratio given by the equilibrium constant. All right? Okay, so that's how we're going to use Q, compare it to K, to determine whether or not we're at chemical equilibrium. Okay, Professor Cummins will be here on Wednesday. I'll see you later in the week.